In metal, the conduction band and valence band overlap, allowing electrons to move freely, which make metal highly conductive. At absolute zero Kelvin, electron feel all energy level from the bottom of the band up to the Fermi level energy EF0. At this temperature, the probability of finding an electron at the energy less than EF0 is 1, and when the energy level is greater than EF0 is 0. The vacuum level is the energy level at which an electron escapes the material into free space. The work function phi is the energy required to remove an electron from the Fermi level to the vacuum level. This explains why metals have high conductivity due to the presence of the free electron and the overlapping energy band. In semiconductor, the valence band VB and conduction band CB are separated by band gap EG. An energy range where no electron states exist. The VB contains the electron involved in bonding within the crystal, while the CB contains energy level where electron can move freely and conduct electricity at temperature above 0 Kelvin. Thermal energy from atomic vibration can excite some electron across the band gap, allowing them to move from VB to CB. These excited electron become free charge carrier, and the vacant position they leave behind in the VB are called holes, which also contribute to the electrical conduction. A smaller band gap, such as germanium, makes it easier for electron to be thermally excited into the conduction band, resulting in higher conductivity. In contrast, a larger band gap, like in silicon, requires for more energy from electron to excitation, so its conductivity is lower at room temperature. The mass action law The mass action law describes the fundamental relationship between the free electron and the holes in the semiconductor at thermal equilibrium. In an intrinsic semiconductor, which is the pure material with no doping, electrons are thermally excited from the valence band to the conduction band, creating equal numbers of electron and hole. So n equal to p equal to ni, where ni is the intrinsic carrier concentration. The law states that the product of the electron and hole concentration is constant, equal in square of the intrinsic carrier concentration, so Np equal to Ni square. This relation holds true for both intrinsic and eccentric semiconductor. Energy band diagram for N-type. Electrons are majority carrier in N-type semiconductor because doping add extra electrons, making N greater than P. N-type doping is achieved by introducing small amount of group 5 elements such as arsenic into the silicon. Each arsenic atom replaces a silicon atom in the crystal lattice and is surrounded by other silicon atoms. Since group 5 elements have the 5 valence electron, form 4 covalent bond with the neighbor silicon atoms, while the fifth electron remain loosely bound and can move freely within the crystal. This extra free electron increase the material conductivity by providing more charge carrier. So N-type semiconductor is the type that N greater than P, where Np equal to Ni square constant. So from this lower diagram, you can see that it make the Fermi energy level or the EFN of the N type closer to EC more than EV. Energy diagram for the P type. When small amount of element from group 3 of the periodic table, such as boron, is added into the silicon, p-type doping occurs. Each boron atom replaces a silicon atom in crystal lattice and surrounded by silicon atom. Since boron have only 3 valence electrons, it can only three covalent bond with the neighbor silicon atom, leaving one bond incomplete. This missing electron create hole. A neighbor electron from the valence band can tunnel into this hole to complete the bond, leaving behind a new hole. The boron atom, after accepting an electron, become negatively charged ion B minus, and the hole acts as a positive charge carrier. This process increases the number of holes in the material, making the hole become the majority carrier in p-type semiconductor. So in p-type semiconductor, p greater than n, where np is equal to ni squared equal to constant. So the Fermi energy level of p-type become closer to EV more than EC. So for no bias case, in the PN junction with no external bias means no external applied voltage, electron from N-type region initially diffuse into the P-type region and recombine with holes. Similarly, holes from P-type diffuse into the N-type side. As electrons leave the N-type, they leave behind positively charged donor ions. As the hole leave the P region, negatively charged accepts ions remain. The process create a region near the junction called the depletion region, which contain no free charge carrier, only these fixed charges. The separation of the charge setup and the internal electric field that oppose further diffusion. Eventually, this electric field becomes strong enough to prevent more carriers from crossing the junction, and the system reach equilibrium. At this point, a built-in potential or the barrier potential exists across the junction and no current flow. Forward bias. In this forward bias p-n junction, an external voltage is supplied with the positive terminal connect to the p-type and the negative terminal connect to the n-type. This creates external electric field that oppose the built-in electric field of the p-n junction, causing the depletion region become narrower. As the result, it become easier for holes in the p-type region to diffuse into the n-type. The electron in the n-type region is diffused into the p-type easier. This increased carrier movement allow the current to flow easier through the junction. The reverse bias. In the reverse bias p-n junction, an external voltage applied with the positive terminal connect to the n-type and the negative terminal connect to the p-type. This creates external electric field that adds to the built-in electric field of the junction, causing the depletion region to be widened. As the result, it becomes harder for holes in the p-type region and the electron in the n-type region to cross the junction. This reduces carrier movement and only a very small leakage current flow due to the minority carriers. This breakdown occurs due to high reverse voltage is applied to the PN junction, creating a very strong electric field within the depletion region. This strong electric field exerts a large force on the minority carriers, like the electron and the holes, causing them to accelerate rapidly. As these high energy carriers move through the junction, they collide with atoms in the crystal lattice, knocking loose additional electrons through a process called impact ionization. This leads to a chain reaction, generating more and more carrier and result in sudden and large increased reverse current, which also known as the breakdown current. Zener breakdown. Zener breakdown occur in heavy dope p-n junction where the high concentration of dopant cause the depletion region to become very narrow. When a moderate reverse voltage is applied, a strong electric field is generated across the narrow junction. This intense field allows electrons to tunnel from the valence band of the n-type material directly to the conduction band of the n-type. A quantum mechanical process known as tunneling. As the result, a sharp increase in reverse current occurs. So the effect of temperature on the breakdown voltage. In Zener breakdown, the breakdown voltage decreases with the increasing temperature. This is because tunneling becomes easier at higher temperature due to the increased energy levels of carriers. The example of this one is like the Zener diode rate of 5.1 voltage at 25 Celsius may break down around 4.9 volt at 75 Celsius. And another type of breakdown is increase with the temperature, means that higher temperature cause more scattering, so carrier lose energy more easily, needing a strong electric field, higher voltage for impact ionization. So the example of this case is like when the diode with an Avahance breakdown at 100 volt at 25 Celsius may break down around like 105 volt at 75 Celsius. Thank you.